So last time we, started talking about biomass, and today we will continue the entire lecture on biomass, and it will again continue in the next lecture also. You know, so today's lecture will be fully on biomass. Now, let us try and understand some terms because these are important. If somebody uses some terms and you may know what the thing is, but you may not know the term. Okay, so it's important that we understand it with that term. Now, firstly, I think that when we are talking about technology related to biomass, one is, of course, we have to look upstream. Upstream means to actual biomass, all right? And then we have to look downstream, where biomass is converted into appropriate fuels, okay? And obviously, when you're looking upstream, there are other important issues to look at. Like, for example, is there any conflict between food and fuel? Because both might be competing for the same land. Okay, so you need to understand those kinds of issues. Okay, and downstream, anything can be converted into anything. The question is, what is the penalty that you pay? In doing that. So obviously, we want to convert it with the least penalty. Okay, so penalty could be that how much of the carbon in my biomass actually ends up in my product. That's if it's only a tiny fraction and most of my biomass has been utilized to provide the energy for the process, then it's no good. And similarly, there could be chemicals that are used in the process, and you need to understand, is it very chemical intensive? Because if it is, then it may not be such a good process. Okay. Now, biomass is typically categorized in in three ways. One is what we call as primary, then secondary, and tertiary sources. Okay, primary is really the actual feedstock which you are deriving by photosynthesis. Okay, and that is the actual material that you are utilizing as the fuel. For example, if it is a woody crop, I mean a tree, then of course you're generating the wood through photosynthesis, so that's a primary biomass. Okay, or if you are usually using oil, all right, from a seed, the oil seed crops, the seeds are primary biomass. Okay, and if, for example, there are certain agricultural residues, which you are generating, okay, which are more like you can say a kind of a part of when you are trying to take out some seed and you're left with something, and then that kind of an agricultural residue is also treated as primary biomass. Okay. Secondary biomass is all the things that you produce, which are created in the course uh, of actually processing a primary biomass. Okay, so for example, I've got wood. Okay, and I saw the wood, and in the process I generate some sawdust. Okay, or I have crushed sugarcane, and I've taken out the sugarcane juice, and I'm left with the bagasse. Okay, so it actually came from the processing of the primary biomass. Okay, and sometimes the difference between an agricultural residue and a secondary biomass of this type is a bit blurred. It doesn't really matter. Some of it you could treat as possibly as secondary biomass. Okay, or let's say when I'm doing pulping of paper, okay, and you create some byproduct liquor, you know, from that process, and which again has certain organic components, you know, which you could perhaps utilize as a fuel in some way, or like let's say if from animals, you know, we derive manure, okay, or like let's say when you distill out ethanol, you know, the liquor that you have left, you know, which is called distillery waste, you know, so those would all be examples of secondary biomass. Okay, now tertiary biomass is after one has used the biomass, okay, and now it is time to get rid of it, okay, and so for example, let's say you are frying something in vegetable oil, okay, and you fry up to a point, and then after that the oil gets a bit rancid, becomes bad, you know, in some ways, and so that would be like a tertiary biomass because it is after it has done its job, okay. Or let's say I have got paper packaging, you know, now you see a lot of it in with all this Amazon delivery and all, there's so much of packaging, cardboard boxes, this, that, you know. So once it has done its job of delivering the your whatever good you had ordered, you know, after that that packaging is a waste, you know. So you have to do something with it, or let's say you're demolishing a house and there was a lot of wood used in that house, you know, so all that debris will become now tertiary biomass. Okay, so yeah, I hope the definitions are clear of primary, secondary, and tertiary biomass. Is everybody clear about the definitions?
Yes, sir.
Yes, sir.
Okay. Now, uh, like, let's say now, let's look at the interface. Now, on the left, you have got biomass, okay? And on the right, you have got bioproducts, you know. And of course, our focus will be really on energy, you know, because this is on renewable energy sources, you know, and so we'll be mostly focused on biofuel and power. Energy means power, you know, and not so much on the pharmaceuticals or value added chemicals and things like that. But those are also bioproducts. Okay. But our focus will be mostly here. And what we really have to look at is how do I go from biomass to this part? You know? And so you have different kinds, you know, of ways of really uh, treating biomass, you know. For example, I could be doing some kind of an anaerobic digestion, you know, or and some of it might require some kind of a pre-processing, you know, before I can do, let's say, some kind of a fermentation or digestion, and we'll see where such pre-processing is required, you know, and those could be either in the form of a chemical treatment or a physical process like exploding, you know, a steam explosion, okay, and downstream after you have carried out your process, you know, you may have to look at how to concentrate your product, you know, how to purify the product, okay. So all that is related to the post processing, whatever you have to do. Now, just like you have biochemical transformations, you could also have thermochemical transformations, okay. And some of the transformations are things like pyrolysis, and we will go through each one of these, okay. So even if you don't know exactly what these terms precisely mean, you'll get a feel for it as you go along, okay. Gasification, okay, and depolymerization, because a lot of the biomass is actually basically what? They're polymeric materials, you know. So you might have to depolymerize, okay, and end up getting products, you know. Those could be probably more crucial, you know, somewhere here, you know, when we are talking about value-added chemicals or pharmaceuticals, etc. Okay, and you could also have not only thermochemical but chemical processes. Okay, like for example, chemistry of lignin, right? How to exactly chemically treat it, you know, and convert it into useful products like maybe surfactants like ligno sulfonates, you know. So those kinds of things would be all chemical processing. But so these are all related to processing. And the core objective at the end is really being able to end up with bioproducts. And as I told you, our focus really will be on the biofuel and energy. Now, let me also tell you that for those of you, you know, who sometimes might be thinking that what should I do after I finish my studies? Well, you know, if you look at the way publications have increased in this area of bioresources and bioenergy, it's really followed an exponential growth. Okay, and so from very limited number of papers around 2000, you know, today, I mean, this is up to 2015, but actually it's been going up higher and higher, you know, and this has become a extremely active area of research. What it also means is that it's not as if everything is all known. Okay, you may be the people who will make things better. You know, things are known, but you have to make it better and better. You know, because only when you make it better and better, finally it becomes technology. Okay, so remember that, and unless it is useful technology, nobody would be interested in practicing such a technology. Okay, I mean, if you just say I've done this, I've done that, you know, but if somebody asks how well did you do it, and you say, well, that was not the objective of my work, you know, then of course, most probably, you know, it will not see the light of the day in terms of a technology. So bear that in mind. Now, we had briefly touched upon this, you know, but let us look at the end of it, if I am looking at biomass for energy, you know, energy and biofuel, obviously what is very important is what was the calorific value of the biomass, you know, what kind of energy content did it have, you know. Obviously, I don't want to take too much effort in processing something with a low energy content. Okay, I mean, anybody would like to process something which has got a high energy content, and so that, you know, the kinds of products that we get out of it will also have high energy. Now, if you look at, there are two axes, all right? The x-axis is the oxygen to carbon ratio. So if you take something like sugar or cellulose, you know, but sugar, say C12, C6H12O6, okay? So now let me ask you, if you had C6H12 and you had C6H12O6, okay, between the two, which would have a higher energy? And if I say express the calorie content per kilogram of product, which would have the higher calorific content?
C6H12.
Yeah, perfect. You know, okay, because you see the oxygens are as if, you know, the fuel has, after all, what do I do when I burn something? You know, gradually it becomes carbon dioxide. So I can think of, you know, as if it is in the process of undergoing a complete combustion, and I am like 1/4 of the way there, or half the way there, or whatever, you know. So obviously, if I'm introducing oxygens, you know, the heating value will go down as I'm adding more oxygens. Okay, so that's what this x-axis is saying, atomic O to C ratio, as I'm increasing, okay, what you can see is that the heating value is going down. This is the direction of the arrow, So this is increased heating value, all right? So as I go to lower and lower atomic ratio of oxygen to carbon, my heating value will go up, okay? So also, now suppose, like let's say if I take the ratio between hydrogen and carbon, okay, all right. So if, for example, suppose I have just coal, C, and if I have got, let's say, methane, CH4, okay, between the two, which will have the higher heating value? Well, it is always the one with the higher hydrogen content. And you'll remember that I said that when your carbon is at the lowest oxidation state, so if I've got CH4, my carbon is at a -4 oxidation state, And whereas when I'm burning it, it is going all the way to carbon dioxide, which has a +4 oxidation state. So I'm really traversing from a -4 state to a +4 state, and in the process I'll release the highest amount of energy. Okay. Secondly, also the hydrogens which are present, they will end up forming water, and that also releases a lot of energy. Okay, the conversion of H to H2O, right? So together, you end up getting a higher heating value as your atomic H to carbon ratio increases. Okay, so when I go this way, my heating value increases. When I go this way, my heating value increases. Okay, low oxygen to carbon and high hydrogen to carbon. All right, that's what happens, and that's why the direction of the arrow is this way. Right, what it means is that heating value increases as I increase the H to A carbon ratio and as I decrease the oxygen to carbon ratio. Okay. Now let us look at some biomass, and and just get a feel for exactly where do they stand, in this plot. Okay, so for example, if I take coal, okay, and coal means I can take something like anthracite coal. Anthracite coal is the purest form of coal. That means it has got primarily carbon, C. And so when it burns, I'll get CO2. Okay. Now, if I, for example, move a bit more, I may come to the a different stage. From anthracite, I may go to coal, and coal is like anthracite, okay, but it is got it's mostly carbonized, okay, but there are traces, of some residual matter, which is there in coal, okay. So coal would be somewhere here, and so it's not absolutely pure carbon, so there would be some amount of hydrogenous material, which would be present in coal. Okay. Now, if I start, again going to, for example, things like I go to biomass. Okay, and now there is a lot of different types of biomass. Okay, and for example, we call all of them as biomass, but they are not all the same thing. Now, for example, if you look at lignite, okay, lignite is for example a type of coal, but actually what you'll see is some amount of material which is traces of plant structure, not as low as in coal, probably a bit higher than that. And if I go to something like peat, it's a brown material which is like as if it's partly decomposed vegetable matter, and you will see the transition between things which look like a vegetable matter, and things which we would probably consider as inorganic, which is carbon, as for example in anthracite coal. Okay, so I think that that's the way in which the thing goes, and so for example here you can see wood. Okay, and these things are specific components, like wood expressed with this black solid square. You look at cellulose. Okay, in cellulose you probably have a little more of oxygen, than in wood. Okay, because wood has also a lot of lignin, and lignin has got material which has got more of carbon and hydrogen and less of oxygen. So wood would come somewhere here, whereas cellulose, may be coming somewhere here with a higher oxygen to carbon ratio. You look at coal. This is all coal. Okay, this is how different types of coal look in terms of what is the oxygen to carbon ratio and hydrogen to carbon ratio. Okay, and when you come here, into anthracite and this area, okay, what you'll find, okay, is that this anthracite, okay, that is very low in both oxygen as well as very low in hydrogen. So it's almost like a pure carbon. So this is really the trajectory, that different kinds of material follows. Now it's also important to mention this because you see, I mean, what we call coal, etc., it has actually come at one time from biomass. It's just that they got fossilized. They got converted into pure carbon. They got all the hydrogen and oxygen got removed. So things like that happened. But at one point, they were all biomass. Okay, so it's very important that we understand the sense of continuity, and you actually see it. As I said, I mean, you look at lignite, you will see traces of plant structure in lignite, so it's not just inorganic, and so it tells you how exactly a plant evolves into becoming a coal or anthracite. Okay, so that's what it is, and this plot gives you some idea of what is their relative calorific values, heating value. Okay. Now let us look at also a little more in terms of a little more precisely on calorific value. Okay. Now you see there are two units in which these are expressed. Like the English unit is British thermal unit. Okay, that is it's still very popular. People will say, "Tell me how much BTU is there in your biomass." Okay, and if I go to the metric unit, of course it will be kilojoule per kilogram or megajoule per kilogram. Okay, and in this it will be British thermal unit per pound. Okay, so typically that's the way in which these things are expressed. Okay, now let us see the relationship between the two. one British thermal unit is really equal to the amount of work that you need to do to raise the temperature of 1 pound of water by 1 degree Fahrenheit, not centigrade. Okay, and you can do the interrelationships, exchange between the two, and what you'll find is that 1 BTU is equal to 1.055 kilojoule. You might wonder, how is it then this is 7.487 and this is 17.636? That's because this is BTU per pound and 1 kilogram is 2.2 pounds. So if I multiply this by 2.2, I'll end up with a value like this. Correct? All clear?
Yes, sir.
Okay. All right. So you can see the how to express the two, in either BTU or in metric system. Okay. Now the second is that you would see over here that they've got a higher heating value. Okay, especially in the metric system they've defined it, the higher heating value. Okay, and also the lower heating value. All right. So does I think we discussed it briefly. Can anyone try to recall what is higher heating value and what is lower heating value?
Water vapor is included in one.
Very good. Water vapor is included. Huh? What did you say?
Yes, sir.
And what does it do therefore?
It takes into account the heat of vaporization.
Excellent. Excellent. Okay. So the normally, like let's say when we burn something, and we said that most of the fuels will have some hydrogen. Okay. Except if you have got anthracite coal, which is like pure carbon, in which case it will only form CO2 when it burns. Okay. When it forms CO2, there's no issue. I mean, higher heating value and lower heating value will be the same. Okay. But if it is a combination of carbon and hydrogen in the fuel, then what will happen is, then when you burn that, okay, you will form CO2 plus you'll end up forming water. Okay. So now what happens is that water, of course, I mean, when you are letting it burn, the water is going off as water vapor, and your CO2 is also going off, so both of them are going off. Okay. But we know that water vapors can be condensed to form water. Okay. Now, if it condenses, what will happen? Once a vapor condenses, what will happen?
It liberates heat.
Very good. It liberates the latent heat. Okay. So what happens is that if I do my operations in a way that I can recover the latent heat from the water, then it is called the higher heating value. Okay, that means I get the sum total, the energy, the lower heating value plus the heat that was evolved when vapors condensed into water. Okay, and also the higher heating value is many times called as the gross calorific value, and the lower heating value is also known as the net calorific value. Okay, so just bear that in mind, and you can see, for example, here you can see that higher heating value 17.636 to 18.519, and this is 16.849 to 17.690. Okay, so obviously the lower heating value is lower because I did not recover the heat from the water that was formed, right? So Now, what this thing does is that it tells you the calorific value of different types of agricultural residues. This is mostly focused on agricultural residues. Okay, and so in most cases, you'll find that, like, let's say these values are not very different. Okay, so if, for example, their basic building block is C6H12O6, then they're not going to be very different. Okay, but if, for example, I have less amount of oxygen, more amount of C6H12, for example, as I told you, the lignin part of it, the the lignin are more of this kind of carbon hydrogen type of materials, so then I will end up with a higher heating value. Okay, now if I come to, yeah, so for example, if I were to look at where do I go, if I look at all of these values, okay, there is not, as I said, I mean, all of these are cellulosic materials. Okay, so they will all be pretty much same. Okay, and now, if, for example, I have things like municipal solid waste, okay, where in fact you could have a much higher moisture content, okay, or refuse derived fuel, so these things will tend to be lower, whereas newspaper, after all, newspaper is what? Is basically cellulosic material. Okay, which is made from cellulose, so they will again be similar to these. Okay, not very very different in terms of value. All right, so now it's very important also for you to know that many people are trying to grow grass as a fuel. So there are certain grasses which grow very fast. Okay, one of those we'll discuss is switchgrass. A lot of work going on in the United States. In this switchgrass, it grows very, very fast. And because it is like cellulose, there's no difference between like sugarcane bagasse and switchgrass. They're more or less similar. Okay, so I will expect to get similar kind of energy from grass as I will get from bagasse. There's not much of a difference. Okay, so just keep this in mind, and of course, at the end of it, which of these you will process will really depend on what is available with you. Obviously, I'm not going to import things from far to process it. These must be readily available somewhere in the vicinity, and then I'm trying to basically derive fuel out of it. So that's really what this thing is. But it's very good that you can, at a glance, see what is the kind of calorific value that different things have. Okay. Now, let me show you an example of a very smart application of the lower and higher heating value. Okay, and although this, of course, was not done with a biomass derived fuel, this work was done with methane, natural gas. Okay, but don't forget, I can also make natural gas from biosystems like biogas. That's also methane. Okay, so it doesn't matter whether it came from biological sources or from petrochemical sources. Methane is methane. Okay, now what did these people do? This is a company, Atul Industries, a very well-known company in our country. They are located in Valsad in Gujarat. Okay, and this is a paper published by their general manager in one of the plants. Okay, now what they did was, you see, earlier, people were using coal, using wood, okay, and burning and generating energy. They needed to run their boiler. Okay, so they need a source of fuel. Okay, so things like coal, etc., were being used. Okay, but at some point they switched over to CH4, natural gas. Okay. Now, the beauty of natural gas is that it's a very clean fuel. That means, apart from your carbon and hydrogen, you don't really have anything else. Whereas coal, etc., it might have some sulfur compounds, some nitrogenous compounds. Okay, and so the kind of volatiles that you'll get when you burn coal will be much more impure. Okay, whereas when I burn natural gas, I only get CO2 plus H2O. Okay, and you can see I get 2 moles of H2O and 1 mole of CO2. When I burn this. Okay, so what is normally done is that when I'm burning, okay, the natural gas, this is my furnace, okay, and water is getting boiled and it is forming steam, okay, and that steam is being utilized by industries. And what happens to the stuff that got burnt, the fuel? It comes out as flue gas. Okay. So what did I have to do? I have to push air. Naturally, I need air because I need oxygen. Okay. So I have to push air to burn this. Okay. But air also has nitrogen. Okay. So effectively, the flue gas that I get will have nitrogen from air. It will have traces of oxygen, the oxygen which did not participate in combustion. Okay. And then it will have carbon dioxide, this carbon dioxide, and then it will have water. Okay. Now, as it is coming out, as it is burning, of course, the temperature is very high, but as it is getting vented out, from the boiler, it comes out at a fairly high temperature, something like 330 degrees centigrade. Now, what is my primary purpose of the boiler? It is to generate steam. Okay, and how is steam generated? I have to heat water. Okay, and I have to heat it, and later on I have to heat it under pressure. So that I generate high temperature steam. Okay. Now, so what happens is that the flue gas is normally passed through a unit known as an economizer, and what it does is that you extract, quite a bit of the heat, from the flue gas, and that is actually going for preheating of your water, the water that I need to feed into my boiler. Okay. Now, after that, what happens is that this flue gas still has fair amount of energy temperature left. It's a high temperature. It has come down from 330 degrees centigrade to about 175 degrees centigrade. Okay. And so what happens is that it is again taken through what is known as a preheater, a water preheater. Okay. And, so over here also, what I'm doing is I'm heating up my water. Okay, and whatever is going into my boiler. Now what happens is that my flue gases, okay, the temperature has got further reduced to about 85 degrees centigrade. And it is at this point that normally people vent it out. Okay. Now at this point, this water is still present as water vapor. Okay. So it is not condensed. So what they did is that they put in a third unit, which is known as a condensing water preheater. Now what this does is that it brings the temperature of the flue gas down to about 50 to 55 degrees centigrade. Okay. Now at that point, the moisture in my flue gas condenses and it forms a liquid. It forms liquid water. Okay. Now, obviously, there is a price to be paid that I required to make some capital investment. I had to put in this unit. But look at the advantage. Okay. When I've done this, okay, I obviously regained the calorific value, the latent heat, because of the condensing of the vapor, and secondly, I ended up getting pure water because the amount carbon dioxide is not very soluble in water, only traces. So, and there's nothing else in this thing. So I get a pretty good quality water, H2O, right? And I plus get this latent heat back, And so, like they've given an estimate, like for a 24 ton per hour condensing boiler, okay? So 24 tons per hour is the amount of vapors that are passing through, okay? The amount of flue gas that is going through, and you can see they recovered 6 million liters of water per year. So that's close to about several tankers of water being saved every day. If you take a tanker which has got say 5,000 liters, in a you can divide your 6 million liter by 5,000 liters, and you'll know how many tanker trips you have reduced. Okay, so I've saved that much in water. And secondly, because I got back the latent heat, they saved in terms of fuel. This is the amount, the normal meter cube of natural gas, which they saved, okay, because of recovery of this energy. Okay, so that is the importance of higher and lower heating value. And naturally, when you are trying to convert a fuel A into a fuel B or a biomass A into a fuel B, just make sure that you are trying to take care of these kinds of losses, and don't let them happen. Because and in fact, another thing, you see, because it is being let out hot, so it is just heating up the atmosphere and contributing to the atmospheric heating. So in three ways, I gain. I gain water, I gain energy, and I cause less heating, of the atmosphere. Okay, so that's the advantage. Did everybody understand this? All clear?
Yes, sir.
Okay. Okay. Now let us go a little further, and I will repeat these over and over again, just so that it becomes a part of you, And so we talked about this briefly, but so if I've got a biomass, biomass feedstock, okay, I can do 4 different things with that biomass, okay. Well, actually, there's a 5th thing that I can do, but this is mostly about thermochemical conversion, but I could also do a chemical conversion or I can do a biological conversion. We're not talking about that here. We are really talking about thermochemical conversion. Okay, mostly where I have to heat it up, to a high temperature, and some amount of chemical processing could also be involved in the process. Okay, now the most basic thing, of course, is combustion. Combustion means that I am supplying adequate amount of air and oxygen in it, okay, so that all of my biomass can burn and burn completely to form carbon dioxide. Okay, that's what combustion is. Now, what happens when I burn this? I am effectively generating very hot gases. Okay, my flue gas, as you saw, okay, but before it came out, it was very, very hot. Okay? And so through a heat exchange with my water gets heated up and ultimately becomes steam, okay, and I can generate process heat, or I can run a turbine, okay, and generate electricity. Okay? That's what combustion is. Okay. Earlier we saw how nuclear power can also give you electricity. It can heat up water, but it was from the release of the some of the radioactive particles, coming out at high energy, which was converted into heat. Okay, but here it is really from the carbon dioxide, which is getting burnt, and the water, that is the carrying the heat, and that heat is what is exchanging with the water. Okay, next is gasification. Okay, now gasification is like a, it's like a controlled combustion. You are not giving all of the oxygen that is required to completely combust, and neither are you depriving the fuel of all of the oxygen, okay, which is what pyrolysis is. Pyrolysis is carried out under anaerobic conditions, okay, mostly. Okay? So there's very little oxygen that is interacting with the biomass in pyrolysis. In gasification, you're partly doing a combustion, okay, and partly you're depriving the biomass of oxygen, okay. That is gasification. And the fourth is that I can actually, most of these biomass tend to be solids, wood, coal, I mean not coal, but all kinds of lignocellulosic material, etc. They're all generally solids. Okay. Now, what one does is that because there is a high demand for liquid fuels, like for example, all the cars and buses, etc., they all run on liquid fuel. Okay, so there is an importance of liquefying, biomass, and so you can carry out a liquefaction. Okay, so these are the four: combustion, gasification, pyrolysis, liquefaction. Now, I of course can end up with different kinds of compounds. Okay, when I do this here, of course, I'm only getting carbon dioxide. Here we will see, when I'm looking at gasification, I can make something which is known as producer gas. In other words, I can generate hydrogen and carbon monoxide, so that can then be fed into internal combustion engines. Even from pyrolysis, I can end up, for example, in some cases forming methane. Okay, or I can end up forming char, like charcoal, like pure carbon. Okay, so that's what I can do with pyrolysis. Okay, and if I've got pure carbon and also if I've got carbon dioxide, I can do very interesting combinations of the two and end up with synthetic fuels. Okay, we will again discuss that. Liquefaction, what happens is that this is a kind of a hydrothermal processing where you have to use hydrogen, as a second component. So I have my biomass and I also put in hydrogen. Okay, and in the process, what I can do is that I can generate actually hydrocarbon type of fuels. Okay, so they would be like fuel oils, which I can generate. Okay, so these are the various types of products which I can get from thermochemical processes. Okay, I hope you can see that. Okay. Now, let us also look at some practical things. Okay? And very, very practical. And many times, what you'll find is that, we want to, our intention is good. Okay, we want to do things, but we don't facilitate what will actually make it happen. For example, suppose, let's say I've got an agricultural field and I've harvested my crop, and then what do I have? All that residue, and it just lies in the field. And what do people do sometimes? they'll just come sometime at night and light a match, and you'll find that the whole thing is burning. Your fuel field, okay? And why? Because they have to create the field for the next round of planting crops. They can't plant the crops with all of these things around. Okay, so they just burn it. Okay, and the ash is useful in the field, so they use that ash. But they're not making any use, of the calorific value of this stuff. Okay, but look at this. It's a simple machine. It's a baling machine. Look how beautifully they compact this stuff. And look at the way. In fact, I used to see a lot of it in England. Every field you see this beautiful cylinder type of biomass. And it's all this stuff. It goes into a machine, a baling machine, and it gets compacted. Need not be only cylindrical. For example, you can see, nice, rectangular shaped biomass and very high density. This is not a low density. This is extremely heavy. Okay, they compact it, and you can see how it is getting compacted here. Okay, now when I have got this, I can actually take it to a power plant because I made it so compact. I can put it in a truck or something and take it, there. Okay, and it can be used as a fuel. But I can't take this because the bulk density is so low. And also you'd require a lot of people and to put it in a truck, and unless I compress it, the cost of running my truck would be very high for the amount of material that I'm carrying. Okay, but here I can. Okay, so what I would say is that all of you go looking around, because many of you will probably come from areas where there's a lot of agriculture, etc. Notice, observe, what are they doing? Can you suggest them something better to do? And exactly the same thing is true about municipal solid waste. Municipal solid waste also, if you can make in a very compact form, right, then a lot of people will take it, will take it and derive energy from it. Okay, so this is baling. Now let me also tell you about a couple of issues, and I believe I touched upon it, but I'll tell you in a little more detail that when we say biomass, okay, it's not just about carbon, hydrogen, and oxygen, okay, or about proteins. All biomass tends to accumulate some inorganics, okay, and when you burn it, then what am I left with? I'm left with ash. And name it, you go and burn wood, you'll find there will be some ash. Okay, now this ash is good in a way because I get back the ash. The ash could have very nice nutrients, because after all, what is biomass? It is everything that the minerals that the ash are all the things that the plant picked up from the field, and it could be some of the fertilizer. For example, there could be potassium residues, which are there. It could be something else, which is an ash. It could be silica, from the clay, etc., which has got absorbed, and a lot of plants have high silica content. Okay, so there are different ways in which I can generate inorganic material in biomass, which when I burn, I end up getting ash. Okay, now ash is a tricky thing. Okay, all this ash looks pretty benign, but depending on the type of biomass that you use, okay, and depending on the temperature at which I am operating my biomass, Suppose I'm heating it to a high temperature for whatever processes, maybe generating power. Okay. Now, what happens is that sometimes the ash can melt. Okay, and it will form a liquid, and it can form what are known as clinkers, for example. And what they do is that when I want to burn something, I have to pass air, and then these things, these clinkers, etc., become an absolute nuisance, and it cuts off the air, and so I will have in sort of incomplete combustion. So I can have all those kinds of problems. All right. Now, so you can see, for example, you can take your ash, and you can make a cone, like for example, out of it. Okay, and then I'm heating it. Okay, I'm heating the stuff to higher and higher temperatures, and what you find is that this cone, you can see it started collapsing over here. There was a little bit of deformation going from here to here. Okay, here it softened. It softened and it kind of fell on itself. Okay, and then it's become more like a hemisphere. Over here, and by the time you come here, it's become like a liquid. Okay, and what happens is that this property of ash can be very detrimental to the thermal process, okay, of your gasification, combustion, everything. Okay, because this ash can have tremendous nuisance value. Okay, just bear that in mind. Okay, so you'll find that ash has basically if you look at ash, look at ash, and what you find is that predominantly it is alkali and alkaline earth metal constituents. So alkali will be things like sodium, potassium. Alkaline earth will be magnesium, calcium, strontium, those kinds of things. Okay, most ash also contain a fair amount of silica. Okay, so your plant actually picks up fair amount of silica from the soil, and then there would be other constituents, which are not these. Okay, I mean broadly, this, for example, is the composition of typical wood. Okay. Now, what is interesting is that the ash, as I told you, is not the same. So, for example, if you take rice straw, India, the amount of rice that is cultivated, so rice straw becomes a very major biomass, which can be utilized. Okay, but rice straw has a large amount of silica. Okay, and the alkali and alkaline earth are there, but relatively smaller amounts, and the others are also there. Okay, but much smaller than let's say in wood. Now notice that this and this, are they similar or not? Similar?
Yes, sir.
Yeah. Now this is the composition of borosilicate glass. Actual glass, which you make from silica and lime and things like that. Okay, and so the borosilicate type of glass and the rice husk ash, are virtually the same. And what it means is that if, for example, you try to use rice husk in a boiler and you're not careful, that the ash might melt and form a glass, and it can completely go and coat up everything, all your surfaces, choke up things. Okay, and it can lead to a real mess. Okay, and of course you can also if you leach out some of the constituents from the rice straw, the soluble constituents, it looks like this, but here also it'll start melting and form a glass. So you therefore need to have a very good understanding of the composition of ash. Okay, when you are carrying out thermal processes, because it can have a devastating effect, on your equipment. Okay, in fact, when I was preparing this lecture, I thought to myself that why not actually produce glass from rice straw? Okay, but I found it's actually been done, right, and done 12 years ago. Okay, and you can see this is a paper, rice straw ash as a raw material for glass production. Okay, so what it means is that there is also you can look at biomass, bioresources, even energy resources in a clever manner, where you might be able to not only derive energy, from that material, but you might also be able to generate some material, interesting everyday materials which we use. Okay, so that would be very nice, because in any case, you see, even to make glass, I'll have to heat it up. I'll have to heat up the raw material to a high temperature. So when I burn the rice straw, I'm supplying that energy, and so I can use it in a very intelligent way and end up making glass. Okay. Now, also this is only one example. I mean, this is not the only example, but I thought I'll mention it. Okay. Now, another term which you should know is what is known as the isopleth. Okay, like for example, if let's say I'm interested in a particular constituent, okay, and let's say I'm interested in the potassium oxide K2O content of my ash. Okay, now obviously if I take an ash where or if I take a biomass, which has got high ash content, and also if that ash has got a high K2O content, then what will happen is my overall amount of K2O will be high, because it's got a high ash content and the ash has got more K2O in it. Okay, and what I'll get is the outermost curve, this curve, right, which basically indicates that something which has got both high K2O and high ash content. Okay, now when I go in this curve, right, what am I doing? Like, let's say, suppose I'm coming to a point where I've got a K2O content of 30%. Okay, but I've got only 10% ash. Okay? Now, on the other hand, I could go to another point where I've got, say, 50%, of my K2O, but now my ash content is only about 5%. Okay, so both cases will give me the same absolute amount of K2O, okay, from the biomass. All right, so these kinds of curves, they signify a point where a curve where the constituent composition and amount is remaining constant, okay, all along this plot. And similarly, I can do this kind of thing for different kinds of biomass, okay, and I can generate what are known as isopleths, so this is one isopleth, this is another, and effectively, it gives me some idea. If somebody wants to is interested in a particular component, can look at the isopleth and immediately come to a conclusion as to which way the person would like to utilize the biomass. Okay, so just keep this in mind. Okay, now when we do a normal combustion with a low tech, normally you don't reach those kinds of high temperatures at which the ash melts. Like for example, in a chula, chula you'll typically find that at the bottom, you'll get ash, but I've never seen liquid ash. Okay, because the temperature is not so high. Okay, you're operating at a fairly low temperature. Okay, maybe around what 500 degree, 450 to 600 degrees at most. Okay, so let's look at, for example, this now. If let's say, so this is a plant, and these are the fruits. Okay, so inside these fruits you have got seeds, oil seeds. Okay, and I can have a deshelling machine which removes this husk, the outer stuff, and it gives you the seed. Okay, from the seed I can get oil. Now over here I didn't really do a processing of this stuff and derive this thing. I just basically deshelled it. So in a way, actually, I would treat it as primary biomass, not secondary. Okay, and yeah, and then you could you'll get this husk. This stuff is coming out. This, and then what you can do is that you can pass it through a machine. This is called a briquetting machine. Okay, and it makes it compact, just like we saw the baling machine, except here that you require to apply very high pressures. And you require some kind of a binder to bind it, and then you might end up with briquettes like this. So you can see this lady using these briquettes, and is lighting a stove. Okay, and it works very well. All right. So this could be a kind of a fuel that you use, and then the ash that you get, you can maybe put it back into the field. If you're close to a farm, then that would be the best way of overall utilizing the biomass through a thermal combustion process. Okay. Now, you could, of course, do things in a more sophisticated manner. Okay. So this is, for example, an equipment for direct combustion. Obviously, this is low tech. You're just putting the stuff in and burning it. Okay. But here you have got much better control. Okay. So what are you doing? You are actually having, this is my combustion zone. Okay. And I'm putting in air. Okay. It's called primary air. This is the first lot of air that is going into my this combustor. Okay. Now I'm feeding my biomass here. Okay. So it is quite far removed from this combustion zone. But what it does is it starts feeling the heat. Okay. As I'm putting it in. So the first operation that will happen is that it will get dried. So my biomass will get dried. And that's very important, because if it doesn't, then my water will soak up so much of the heat, and unnecessarily that will be wasted. So I might as well dry and get rid of all that water, before I come to this place. And if there's too much water, you may not even have combustion. Okay, so it gets dried, by the heat that is flowing towards the left. Okay, and so now it's burning. Okay, but when it burns, it never burns completely, because if, for example, there are fine particulate matter, it can get just carried away by this flame, So all of it may not be burned. My airflow may not be adequate, so it may not burn. Okay, some amount will be left over, but some amount might get carried away. And if this is what is soot, we know that this is what ends up as soot because a lot of unburnt matter, which is there. So what you do is that you have a secondary air. So you are doing a post combustion, okay, and you're making sure that those fine unburnt materials are getting burnt more completely, and so that's a very nice way of reducing the soot formation and also deriving more energy, from your biomass. Okay, now over here it is burnout, means basically the fuel has exhausted its calorific value, and I've got ash, which is basically flowing. Now, if the temperature is high enough, it could be in the form of a slag, like a liquid, and it starts coming down. Okay, and so you may need to cool it. Okay, so it cools, and finally, I get ash collecting from here, and I utilize the energy, from my combustor in doing whatever work, etc. I want to do. Now, one of the things that you have to remember is that it looks very benign. This also looks so cute, everything is fine. But sometimes, we don't realize that you could be actually generating very toxic substances, okay, in the gaseous stream, coming out along with your carbon dioxide and water and everything, and one of those is dioxin. It's one of the most carcinogenic substances. Okay, and this is, although it is basically tetrachlorodioxin, this is typically known as dioxin. That's the very common term that is used for this. Okay, and now dioxin formation is critically dependent on the temperature at which this whole thing is running. Okay, if the temperature is too low, then you might actually end up with high dioxin formation. So in this, you may not realize, that you're doing any harm, but it could be that there's a fair amount of dioxin that is coming out. Okay, and so people will obviously start looking at the kind of temperatures, which are optimum for combustion, and make sure that the dioxin formation is minimum. Okay, that's vitally important. Now, this is one of those, for example, which allows for a better quality of combustion. Now this is known as a fluidized bed combustor. Okay, now has anyone heard the term fluidized bed? Are you aware what it is? Now, what you do is that you create, okay, a bed over here, okay, some kind of a granular bed of something, and you are passing air, from here, okay, and this biomass, what you do is that you kind of make it almost powdery, okay, so that it becomes very fluffy, and so in the presence of air, all of it starts floating, all of this stuff, and it looks as if it's a liquid, and that's why it's called fluidized. Okay, the air goes and sees this each of these particles very intimately. Okay, so the combustion that takes place is wonderful. It's almost complete combustion. Whereas, many times what can happen is that you'll find that you're burning wood. Okay, the outside is burning nicely, but inside, when you see, it's all kacha. It's not burned. Partly because the ash is coating, and is blocking off the access of the inside to the air, and also because the wood may not have adequate porosity, to allow the air to go deep inside. And so, you have a lot of unburned matter. Okay, but in a fluidized bed, okay, what you have is this excellent fluidizing. Okay, and so effectively, it's fluidized in a way that your some of the stuff actually will flow over here, and it will come out as ash from this side. Okay, and of course not all of it. There will also be some combustion ash which will come out from here, and but some and substances that with this kind of fluidization, the quality of the combustion is very good. Okay, and typically, you can burn things very completely, right, with excellent heat transfer, and you can minimize the formation of your dioxins, right, and also you can minimize formation of things like NOx, nitrogen oxides, because NOx is typically formed from the oxidation of nitrogen in air. Is not from nitrogen in your biomass. It's basically the nitrogen in the air that leads to NOx formation. And typically, if your temperatures are too high, then also your NOx formation can be high. And so you can actually do a very complete combustion and yet kind of keep your temperatures controlled to less than about 950 degrees centigrade. Okay, and that is the most optimum combustion that you can get. Now, in fact, the EPA, the American Environmental Protection Agency, they did a very nice study in 2003 where they burned municipal solid waste, in an incinerator. I mean, these you can think of as incinerators, okay, with a conventional incinerator, okay, and another where they had a fluidized bed incinerator, like this, okay. And what they found is that the dioxin formation in the conventional incinerator was about 7 times as much as in the fluidized bed incinerator. So obviously, from a not only from the completeness of combustion viewpoint, but also from the health viewpoint, this would be an ideal kind of a combustor or an incinerator. But then, these things generally will probably be more expensive, so your capital cost, etc., will go up. So you'll pay a price, somewhere. Okay. And secondly, your biomass, you might have to, as I said, you'll have to grind your biomass to a fine powder, and so that again requires a lot of energy, to grind up things like a sawdust, and so one needs to be very careful. But say if I'm getting sawdust, obviously I'll try to use a kind of a fluidized bed incinerator, because my sawdust is already in a dust form. It will be easy to fluidize it. But if I take otherwise things like wood, etc., it will be very, very costly to try and grind it up to a powder. So there are pros and cons which you need to understand. Okay, now let us look at going from combustion. Let us go to gasification, right? As I said, in combustion, you end up with only carbon dioxide and water. So it's completely gone to the +4 oxidation state of carbon, okay? And all the water has come out as water. Now, in a gasifier, you do something different, okay? So let us try and understand what is done in a gasifier. It's not miles away from a combustor, but very, very interestingly arranged. Now, this particular one that I'm showing you is what is known as a downdraft gasifier, means the fuel is falling down and your air, you know, is basically traveling up. Okay, your air. Okay. Now, over here, what happens, and finally, your fuel and your product, you know, whatever is your final fuel that you're trying to make, a gaseous fuel, both are traveling in the same direction. Both are traveling down. Okay. Now, I am passing the air over here, so this tends to be my hottest zone. You know? And so this is the place where I'll have oxidation, means combustion. You know? I'll basically convert carbon into carbon dioxide, you know, in this particular zone, the blue zone. Okay. I'm feeding my fuel from here. Okay. So what happens is that two things happen. One, of course, because of the combustion, heat is traveling up, you know, and so it is drying my fuel. Okay, just like we saw in the previous case. But another very interesting thing happens because my air is getting is reacting with my fuel over here and becoming carbon dioxide. So my air is getting depleted in oxygen. Okay, so it doesn't really, you know, over here, what you have is like a heating of a pyrolysis nature. Okay, because why pyrolysis? Because that's what I have. I mean, I'm not really, I don't have much oxygen left. My air has got combusted. So obviously I have to control my airflow accordingly. Okay. Now, what is pyrolysis? Typically, as we said, like if you take like a sugar, you know, or you can take starch or something, C6H12O6, and if you look at it, that if you were to remove the H12O6, that is like 6 molecules of water. Okay, so what will I be left with? I'll be left with carbon, you know, and my pyrolysis. So drying is different. Drying is if I've got moisture in my fuel and that is getting dried. Pyrolysis is I'm actually carrying out a chemical process, you know, and it is dehydrating my fuel and leading it to char. Okay, so that is pyrolysis. Now something very interesting happens. Okay, that I have generated carbon dioxide here and I've generated carbon here. Okay, now so I can have very interesting reactions. Okay? And combustion also gives me water because my fuel has water. My water is also traveling. So I can have a reaction between carbon and carbon dioxide, which forms carbon monoxide. I can have a reaction between carbon and water, which gives me syngas, carbon monoxide plus hydrogen. I can also affect the water gas shift reaction. Okay, that means you know, carbon monoxide which reacts with water, and I get some CO2, and so I might be able to increase my hydrogen content, you know, in this manner. Okay, and plus I could have, okay, because I've got carbon, because I've got hydrogen, and because my air is now depleted in oxygen, I could also have reactions like this. Carbon plus hydrogen going to methane, carbon monoxide plus hydrogen going to methane plus water. You know, this reaction is of course endothermic. You know, so it requires high amount of energy. So chances of it forming will be less. But yes, this can go. You know, you can see it's a very exothermic process. You know, so I end up with then what? I end up with things which are gaseous, and these are fuels. Okay, I can end up with syngas, and I can end up with methane, and I can also and of course there'll be some amount of water, Now this thing, of predominantly syngas plus some amount of methane, this whole thing is known as producer gas. Okay, this is what is producer gas. All right. So, just keep this in mind, that, these things can, that some of these reactions are endothermic and some of them are exothermic. Okay. And I think that the way these people have written is by plus, they mean that heat is released, because they're talking about it as exothermic, and by minus, they mean that heat is consumed, Okay, so they have probably altered the signs, from the conventional signs as we know it, because we know that hydrogen and oxygen will burn to form water, in a spontaneous reaction. So what they mean is that it liberates heat. So by the plus here, they're talking about liberating heat. Okay. Now, in this gasifier, what you have is you have two types of gasifier, actually three types. The one that I first described to you right now, that is known as a downdraft gasifier, where basically, as I said, the fuel and your product, are both flowing in the same direction. Okay, everything is flowing in the same direction, and you can see the ash coming out from here, and your gas is coming out from here. Okay, now in this particular case, okay, this is one, and then you have what is known as an updraft gasifier. Okay, in the updraft gasifier, what happens is that my oxidation zone, where my combustion takes place, is right at the bottom. So this is my hottest zone. Okay, here my hottest zone is here. Okay, here my hottest zone is here. Okay, and what happens is that in this particular case, what has been found is that you can actually take biomass which has got more amount, of water, it can tolerate up to 40% of moisture, it can tolerate more ash. Okay? In this particular case, it tolerates less amount of moisture, something like 10 to 25%. Okay, and there is less amount of tarry matter, in the gas that is coming out, this producer gas, because after that you have to again clean up that gas, because you get a lot of tar formation, and the tar tends to get carried along with the gas, so you have to separate out the tar, Okay, and in this particular case, what typically tends to happen is that the amount of tarry matter, tends to be more and more, because my combustion zone is right at the beginning, and the tar tends to form here, and so I have no control. Whereas over here, some of the tar which was formed, it can be cracked open during the oxidation in the combustion. So I end up with less amount of tar traveling with my gas. But in this particular case, once it has crossed the oxidation zone, the tar just keeps building up, and it ends up with your product gas. So it requires more cleaning. But then the advantage is that it can tolerate more moisture, and it can also tolerate more ash. Okay, so this is the updraft gasifier, and this is the downdraft gasifier. You can see in this particular case, the maximum, this is the temperature. Okay, the maximum temperature, okay, is basically around the combustion zone. This is my combustion zone, oxidation. So naturally the temperature is highest here. Over here, the temperature is highest here. Okay, and this is the concentration profile of pyrolysis products in the gas. And over here, what happens is that it increases and then it goes down, because as I told you, some of these pyrolysis products, will tend to get cracked in the oxidation chamber, whereas here it just keeps building up. And that's the reason why more tar gets carried along with your producer gas. Okay. Now, exactly in the same manner as we saw the fluidized bed combustor, incinerator, you can also have a fluidized bed gasifier. Okay. I'm not going to go into the details of it, but obviously, and there's a very interesting setup here that the combustion gases, the CO2, etc., a lot of the exhaust gases tend to be taken out from a separate outlet. In this particular case, they have designed it very cleverly, whereas the gasification over here, which takes place, it's mainly the producer gas which travels in a separate outlet. And because of that, you tend to have a much richer producer gas, free of carbon dioxide for the most part. Whereas here, there would be a lot of carbon dioxide, which may also be present in case some of the CO2 did not get converted into CO, if the gasification did not take place. Okay? And so this is all typically how you do gasification. Okay. Now, let me actually show you, in fact, a unit which was built by a colleague of mine, and so this was actually you put biomass from here. This is the hopper, okay, and this is your gasifier, and this is your producer gas coming out. Okay, it's got calorific value, so you can actually burn it. You can see the flame, okay, or you can actually operate this in an internal combustion, engine, and you can generate power. Okay, so you can see electricity being generated, from the unit. Okay, so you can generate electricity or you can generate heat, whatever you want, and the gas, as it is coming out from here, it's a very drawn out process. You need to, as I said, eliminate tarry matter, because otherwise you will completely choke up everything. Okay, you need to separate out particulate matter. There are unburned things, which will come out. So you need to take those out. And also, there will always be some amount of water production, as we saw. So you need to dry the gas. So these are the operations that you will do after you have done your gasification. Okay, and so there are various kinds of units over here. Feed hopper, air inlet, this is the reactor, scrubber, to scrub out tar, there are separators, cyclone separators to separate out different fractions, you have a filter where all the tar gets collected, etc. I mean, don't have to go into the details of it. And the efficiency of your heating or the efficiency of your gasification is what is basically whatever producer gas you produce, whatever is coming out from here, whatever is the heating value of that, or the calorific value, multiplied by the total amount of producer gas, let's say coming out per minute, okay, or per hour, and divided by whatever was the heating value of my initial biomass, okay, and multiplied by the total amount of biomass that I fed. So one divided by the other multiplied by 100 is my heating value that I got from my gasification process. Now, normally what will happen is for power generation, the conversion of thermal energy to power is what, about 30%. So obviously, if I were to just look at power generation, the value would be much less. This is only for the heating value in the producer gas, not producer gas going to electricity. That would be a separate efficiency computation that you have to do. Is it clear to everyone?
Yes, sir.
Okay.
Yes, sir.
And you of course, when you go deep into the subject, naturally there is a lot of design. Okay, and we are of course not going into those aspects in the course, but for that you need to understand each and every reaction in great depth. You need to understand the thermodynamics of the reaction. You need to understand the kinetics of the process. Okay. And you need to understand what are the constituents that are being formed. What do I have to do in terms of post purification? All of that stuff will need to be worked out. How much is the moisture content? What is the range of moisture content in my biomass that I should consider? And so this part of that analysis is known as proximate analysis, where you get some of the gross values, like how much is the carbon percent, what is the volatile matter, how much is my moisture, what is the ash content, okay? All that stuff I get over here. And here, what I get is I get more of the elemental analysis, because you need to know, for example, is there sulfur in my fuel? Will I have a problem? Will I get SOx emissions? What will happen to NOx? Okay, so I need to do the analysis. I need to know the calorific value, of my fuel, so that I can design accordingly. Okay, because there should not be an explosion, right? You have to be very, very careful, right, while developing this, that it can withstand the pressures that will be generated, and that in turn will depend on the calorific value of the fuel. Okay, so this is how you design. You can ignore the drawings; no questions will be asked on that. Okay, now so this is, for example, an actual data. All right, maybe I'll pass on this paper so that you can study it. So what did we say is formed? Once I've dried the producer gas, the water is gone. Okay, all right. And assuming that all my carbon dioxide was completely utilized in the reaction with carbon, then all my CO2 will get converted into CO. Okay, so I will effectively have CO, CH4, and H2. And I should not have anything else. Okay, and so this is what I'm then feeding into let's say an internal combustion engine. Okay, and what you have to do is that you can do gas chromatography and monitor, okay, how these individual constituents are changing, okay, over time. I've fed my biomass, how these things changing, and from the way these things are changing, you can figure out, what is the kind of reaction, the relative kinetics, etc., that is taking place in the different zones. Okay. Also, I will come to know whether I am getting a steady output, or is it fluctuating. Maybe if it's fluctuating, there is some problem somewhere, which one I'll have to look at. Okay. So you monitor, the gas composition, okay, as a function of time, and just see, what is the level of steady behavior, that you're getting. This is methane, this is hydrogen, and this is carbon monoxide. Okay. Now, and then, you can, by integrating this, okay, that's how you will find out what is your, because I know what is the calorific value of these things. Okay. From the percentage, I know exactly what is the sum total of these their calorific value. So and that's how you calculate this efficiency, the heating value. Okay, so I get the heating value of the individual constituents, and from that I can calculate. So you can see the producer gas efficiency in terms of the total amount of calories which were there in my biomass, to what was the percentage of it conversion, how much of that calorie ended up in my producer gas is pretty good. In this particular case, it's about 64.8%. Not bad. Okay. And you can see now when I am generating power, the efficiency of power generation will be something like 35% from the producer gas. In other words, what am I doing? I've got my power generation efficiency as 24.5%. Okay. So you'll find that generating power from producer gas, roughly about 35 to 40% is the efficiency of the conversion. Okay, now let me also tell you some remarkable things which people are doing with biomass. Up till now, we have talked about generating heat. We have talked about generating heat from a combustor, or generating heat from producer gas, or generating electricity, from the producer gas. Now, because we saw that the producer gas is primarily syngas, so you can actually carry out, reactions, okay, where we know, for example, that this is your syngas. So I took some cellulosic material, let's say, and I generated syngas through gasification, okay, and in case I've got too much of water and CO, I can also carry out the water gas shift reaction and generate more hydrogen and CO2, and I can even scrub out the CO2. I can do a correction, as is required. Okay, and now there is a well-known reaction which is known as the Fischer-Tropsch synthesis. Okay, I'm not going to go into the details of the Fischer-Tropsch synthesis, okay, but I expect that you will read it up, where I can convert syngas into hydrocarbons, okay, just like diesel or petrol. I can make this stuff. So I can actually start with biomass and ultimately end up with just standard fuels, like diesel and petrol. And you can see this company, all right, and this is BTL. BTL stands for biomass to liquid, okay, biomass to liquid production, and they've called it sun diesel, so they were making diesel out of it, okay, and just look at this data. They're processing 2 lakh tons of biomass, 200,000 tons, okay, and look, this is the fuel that they are making, right? And from that they need biomass which is 10 lakh tons, 1 million tons. Okay? So they're taking 1 million tons, and where I'll get 1 million tons? Firstly, it'll have to come from some farm, and so the farms are going to be spread all very far to have 1 million tons of biomass. So unless I do that baling, so you can see how it is baled, brought. This is now their feedstock instead of coal, okay, instead of oil, and they're basically effectively converting it into diesel, right? Now, the carbon balance is very interesting. This is another term that you should know, okay? That is how much of the carbon which was there in my initial biomass, how much of that is ending up in my product, right? So here it is 42%, 0.42. So 0.58 got lost. Where? In combustion. Okay, the amount of carbon dioxide that I generated, I vented out a lot of the CO2. And only the rest of it basically became my syngas, and from which I got this. So, there's a large, obviously there's a much higher amount of energy that I had to produce from combustion, and release it as CO2, and what was left was 42%. Okay, so just so that you have an idea of how biomass is converted into liquid fuel, and in this particular case, into diesel. Now let's come to pyrolysis. What did we say? Pyrolysis is really it's an anaerobic process, right? And you're really doing it under a reducing environment, okay? And it generates, of course, in the process there is heat that is required, okay? So most organic biomass will have certain volatile materials, all right? So in the pyrolysis, two things happen. One is that all the volatile substances get removed, okay? They're taken away. And the second thing is that, as we said, that any of these cellulose or carbohydrate type of materials, if you remove water, then you're just left with carbon. There's no change in oxidation state. It goes from a carbon 0 to carbon 0. Okay, C6H12O6 or its polymers are all carbon 0, right? Because each oxygen is -2 convention, -2 into 6 is -12. Each hydrogen by convention is +1. So +12 and -12 will cancel out, and my carbon will have an oxidation state of 0. And in elemental carbon also it is 0. Okay, so there is no redox process, that takes place during pyrolysis. Okay, and all the volatile matter is removed. Okay, volatile matter is removed because sometimes this volatile matter can create a safety issue in some of the applications where you require just a form of carbon. Right? Now, this is some data, right? And most of the data is from Brazil, right? Where what they have shown is that in a conventional kiln, okay, where you do pyrolysis, you typically will, suppose you take about 4.5 tons of wood, you'll end up with about 1 ton of charcoal. Okay, and you can work it out because you are getting rid of the oxygen and the hydrogen, so there will be a loss of weight, plus some of the wood you have to burn to generate the heat that is required for the process. Okay, and that will go up as CO2, right? So overall there will be a reduction in weight. And in one case, and I might ask you some questions around it, in the modern kilns, it's about, you require about 3.6 tons of wood to make 1 ton of charcoal. Okay, that's effectively the carbonization process. Now, let's try and see, what a tremendous role this plant-based carbon has had on the steel industry in Brazil. So, since 1920, they've been producing steel with charcoal, in Brazil, and that charcoal is derived from plants. Okay, and look how much they're manufacturing 7.8 million tons, and this 2002. So today maybe it is about 12 million tons, of their production of pig iron, which is the crude iron from the smelting process. Okay, and the entire charcoal comes from eucalyptus forests. Okay, so in Brazil, it's very interesting. I'll show you in one slide. Um, they are continuously cutting down these trees and they're planting, and they have struck a balance between how much they should cut and how much it will grow, so that they have more or less reached a steady state, in terms of not destroying their forest, in making this. Okay, and large number of people, 240,000 people were involved in this activity. Okay, of basically making the charcoal, so people who grew plants, who cut plants, who converted it into charcoal, it's a massive operation. Okay, and it's all coming, their primary energy is coming from the forest. Okay, now this is in fact a photograph that I had taken in Brazil. You can see these trees, and there are thousands and thousands of these. They get cut every day, okay, and they are replanting. All of it doesn't go for steel. In fact, when I talk to these people and I ask, where is all this going to go? And I found a huge market, is going to the United States to make toilet paper from this. So everything is not for energy, they make a lot of paper and things like that from this. Okay, it's a massive industry, one doesn't realize. Okay, so if you can cut and grow at the same rate, then it becomes a renewable resource. If you don't do that and you're just cutting and not growing at the same rate, it's a non-renewable resource. Okay, as simple as that. All right. So you can see that of course it is possible because Brazil has it has got a huge land mass. Okay? Brazil is much bigger than India, and it has got what, about not even a fourth of our population. Okay, or about a fourth of our population. So they've got maybe 3-4 times the amount of land, and they've got 4 times less population, and it's very fertile land. And so obviously, they can do things there which we may not be able to do. So while it looks interesting, okay, but keep that in mind. All right, that it may not be that simple to replicate this kind of thing in India. And but Brazil and India are collaborating, in how to take some knowledge forward together. And I tried to show you, that when they cut 1 ton of stem wood, and the growing biomass, okay, what is the typical amount, of the biomass that they effectively generate. Okay, let us look in now. If I have to go to low tech, what we discussed is very, very huge kilns, obviously making millions of tons of charcoal, but people also in India make charcoal in very small scale. Okay? And they make it from all kinds of material. You can see leaf litter, sugarcane trash, rice husk, coir pith, groundnut shells. All of this, okay, is used. Okay, and you need basically a container where this process is taking place. That is a carbonizing chamber. That's where you generate the charcoal. And then because it's in the form of a powder, it is pelletized, it's granulated. Okay. So for that, you need some kind of a binder and a briquetting machine, which can pelletize it. Okay. And so stepwise process, is collecting, of course, the biomass, and then you chop it up into proper size. Okay. And then you just allow it to dry in the air, in sunlight. Okay. So you just let it dry. Okay. Then what you do is that you take a drum. Okay? So this is something that any of you can do in your house, not in your house, but maybe in a farm or somewhere. Okay. And so this outer drum is basically where combustion takes place, and you generate the heat that you require for pyrolysis. Okay. So that's what is going on here. Now inside that drum, you put another drum. Okay. And in that drum, what you do is you also have some holes, etc., which are pointing down, and that all allows the volatiles, to effectively escape, from that drum, the inner drum. Okay. And the rest of the material is basically getting converted into char. Okay. That's what you have. All right. And because it is a closed drum, so there is very little air, which is entering this. So it provides the anaerobic condition that you require for char formation. That is for pyrolysis. Okay, that's effectively what you have. So outside drum, of course, air is coming, is heating up, but the inside drum is protected from air. Okay, so you can see outer drum, 200 liters metal oil drum with a top cutout and a 12-inch width into this hole cut in the lower side. This one. Okay, 2 iron rods are fixed at the bottom of the metal drum, running parallel from one side to the other, and that is to place the inner drum. Okay, so the iron rods act as a base. It supports the inner drum. Okay, and in the inner drum, it's about 100 liters, say, capacity. Okay, and there are holes in the bottom, and those holes allow the volatiles to escape, from the bottom. Okay, and you just place the inner drum inside the outer drum and carry out this process. But these processes also, let me tell you, the pyrolysis processes sometimes can take a lot of time. Like in this particular case, I think somewhere it takes about 30 days, to actually complete the whole process. So it's a time-consuming affair. It's not something that happens right away. Okay. Then you look at it, the carbonizing the biomass. Biomass is tightly packed in the inner drum and fired for 45 minutes to 1 hour. Okay. After firing, the carbonized biomass in the inner drum has to be collected and weighed. In this method, 30% of carbonized char can be obtained. So from 100 kg, we are getting about 30 kg. Okay. The binder material is used for strengthening the briquettes. For every 100 kg of total weight of carbonized charcoal, they add about 5 to 6 kg of flour, and that is the binder. They mix it up, and then they briquette it. And I showed you a briquetting machine before. Okay, so you can just briquette it and make uniform size pellets. Okay, and then those are dried and packed, and those are your charcoal granules which you get. Okay, now and typically you can see the characteristics of the briquette. There's still some moisture, about 7%. There is some volatile matter, but the fixed carbon, the carbon weight is close to about 83%. Right? There's very low ash in this system, and sulfur content tends to be low, and you get a very high heating value, from this charcoal. Okay, keep that in mind. Okay, now what I will also do is maybe, sorry, can someone tell me why you make charcoal? What is the advantage of charcoal over biomass?
More carbon content.
Yes, more carbon content, and it has got a higher calorific value. Okay, so transportation becomes easy. Uh, but there are other reasons also that, charcoal actually burns very cleanly. You get a very clean flame out of it. So, from the pollution angle also, it is much better. So those would be some of the main reasons. And also, let me tell you, some of the charcoal can also be converted into coke. You know that for making stainless steel, let's say you need coke, right? Because stainless steel has carbon in it. So you can actually provide that carbon, the coke, actually in the by basically taking a kind of charcoal and then converting it into coke. So those are the importances of effectively having charcoal. Okay? And another, that transportation cost is much less, because I'm transporting something with a higher calorific value. So obviously that is preferable, because many times you have to transport these over long distances, and so that becomes important. Okay? Now let us go to the last part, which is the biomass to liquid. Okay, I'm talking about thermochemical processes. Okay, now this, of course, as I told you, is of great importance. Okay, now it's possible that in the long run it may not be so important, but as of now it is certainly important, because India spends so much of money on buying petrol and diesel, or all the crude oil, and getting this. And so if you can get it from your renewable sources like biomass, that would be nice. Okay, so it's important that we try and understand the process of converting biomass by this hydrothermal liquefaction. Okay, so that is what HTL stands for, hydrothermal liquefaction. Okay, now, so what are we doing? As we said, hydrothermal means that you also require hydrogen to carry out this process. Okay, so that's one drawback, because then you'll require hydrogen, and that hydrogen has to come from somewhere. Okay, now the other problem with this is that you require very high pressures and temperature. Temperature not so much. I mean, combustion has higher temperature, 350 degrees centigrade, but look at the pressure that you require, 3,000 pounds per square inch. Okay, that's huge. Okay, we are talking about close to about about 220 bar pressure, that kind of a pressure. So that and then what that means is that I need equipment, which can withstand that kind of temperature and pressure. And when you're talking about biomass, you're talking about such large volumes that you can well imagine what might be the cost, of making such a reactor. Another issue is that, you see, if you operate in a batch process, it becomes prohibitively costly, because you'll have to heat, and then you'll have to cool, you have to take out the mass, and again you have to feed charge new biomass, again repeat the whole process, and to make it a continuous operation is not a trivial task. How do you basically do a continuous operation maintaining the reactor, in this kind of a thing? I mean, that's where the ingenuity of engineering comes in. Okay. All right. Now, the other thing is that, this hydrothermal liquefaction is actually carried out in in water. Okay. In fact, I'll show you what kind of water is required to carry out this process. Okay. Now, the point is that so it's carried out in water. So what would be one advantage of this hydrothermal liquefaction as compared to, say, combustion or drying or pyrolysis? Can you think of one advantage? I've told you all the disadvantages. Tell me one advantage. Can you think of an advantage?
And there are no greenhouse gases generation. CO2 is not there.
No, there will be, because to generate that kind of temperature and pressure, that energy has to come from somewhere, no?
Yes, sir.
You see, because this process is carried out in water, so I can actually use a wet biomass. I don't need to have a dry biomass. You understood? Okay. And we have seen like municipal solid waste and things like that, they've got 40-50% moisture many times. Vegetable waste. Okay. Look at all the vegetable waste. I mean, it's got very large amount of moisture. So if I do HTL, then it doesn't matter. Even if my biomass is wet, right? So I can take wet biomass and do the process. Okay. Now, when you do this, what happens is that under those conditions, the biomass, effectively it gets converted into a bio crude product. So this is, you can see oil, right? This is a bio crude. Okay. And you also have, naturally, because I had water, okay, at of course these conditions, but that aqueous part, is generated, but some amount of the organics will be also dissolved in my aqueous phase, So this actually then becomes a good source for doing gasification chemistry. So I can do either hydrothermal gasification, or maybe in some cases I might be able to make biogas, by some kind of a fermentation process, Okay. So, and then once the organics is all taken away, then I get clean water again, and that water can be recycled in my process. Now, this bio crude oil that I get, this is the one where I then do a catalytic hydrotreatment with hydrogen, okay, at high temperature in presence of a catalyst, okay, and it can then, like if it's a oil with a long chain, it can be broken up into smaller chains, okay. If it is an oil which has got carboxylic acid groups at the ends, like a fatty acid thing, you can split it, and all the CO2 can escape. So I can end up with simple hydrocarbon fuels, by this kind of a catalytic treatment, okay, hydrotreatment, right? And the hydrotreatment is required. I need hydrogen because there is a lot of oxygen in my biocrude, and they have to be taken out. So when I have got hydrogen, I can take them out as water. Okay, that oxygen can combine with hydrogen, react and form water. I could have a lot of olefins, and then the olefin, okay, can be hydrogenated, reduced to a saturated hydrocarbon. Okay, or if I'm cracking, okay, then obviously if I crack into say two parts, then the two parts will be like radicals, right? I'll still need hydrogen, okay, to combine with those radicals. Say I've got two radicals of carbon and I've got a H2, I can combine, and so I'll generate smaller chains which are saturated. Okay, so that's why you need hydrogen in the process. And once I've got my oil, this kind of crude oil which has been hydrotreated, this is called a hydrotreated biocrude. Okay, and then I can do a fractional distillation, just like you do with crude oil. What crude oil you get from Middle East, all these refineries, what are they doing? They're basically fractionating to gasoline, to diesel, to jet fuel, which have different kinds of molecular weights, compositions. Some will be cycloalkanes, okay, all that kind of stuff you can do. So this is the process of converting biomass into liquid. Okay, now let us try and see. I told you that 350 degrees centigrade and 3000 pounds per square inch, which is around 220 psi, and we had seen this graph before, so you are talking about, like, let's say if you're talking about say 1 megapascal is about 10 bar. Okay, 10 megapascal is about 100 bar. So you're talking about you're talking about a pressure around here. Okay, around here, which is about 220, 30 bar. Okay, now and look at what did we say is the temperature? 350. Okay, so 350. So this is the point near to the critical point of water, right? Almost going towards the supercritical state, right? And so you can imagine what a horrendously complex task it is to create a reactor for this kind of a temperature and pressure, and for that kind of a scale of operation, where you have to process, say, millions of tons. And that's why, these things are all great, but, it's been almost impossible to commercialize, these kinds of processes. Now, there is another very interesting property of water, which I thought I will point out, which is important for the biocrude oil formation. What is the dissociation constant of water? Well, it's 10 to the power minus 14, means H into OH. Okay, I mean, if I've got plain water, right, I'll always have 10 to the power minus 7 molar H plus and 10 to the power minus 7 molar OH minus. Okay, that is the dissociation constant. So the product becomes 10 to the power minus 14. Okay, and that's why the pH of water is 7. Okay, and the pK is 14. Okay, of water, because minus log of 10 to the power minus 14 is equal to 14. Everybody clear?
Yes, sir.
Yeah,
Yes,
but
sir.
that is the dissociation constant of water under normal conditions. Like say under ambient conditions, or even if you take boiling water or steam, etc., it will not be very different. But what happens is that water, when you start heating it up, okay, and let's say it comes to a temperature of around 300, or around here, okay, what happens is the dissociation constant value is increasing, okay, and therefore my pK is coming down. It's 12, means I've got now 10 to the power minus 6 into 10, or here, if I'm here, it will be about, say, about 10 to the power minus 5 into 10 to the power minus 5, which is 10 to the power minus 10. This is 11, say, or somewhere thereabouts, between 10 to the power minus 5 to 10 to the power minus 6 molar is my H plus, and 10 to the power minus 5 to minus 6 is my OH minus. What it means is that under those conditions, water is more acidic than the normal water as we know it. Normal water is neutral, okay? But the water under these critical, supercritical conditions is got more acidity as well as more alkalinity, okay? And so it can become, you can actually induce acid and base catalyzed reactions of this biomass, okay, like breaking it up, this, that. You can do all kinds of things which you normally would not be able to do. Okay, and that is one of the important reasons why I need this kind of an operating temperature and pressure. Okay, is it clear to everyone?
Yes, sir.
Okay.
Yes, sir.
All right. Now, so this kind of a process, for example, has been used like, I'll show you later on, some of the work done in India on making jet for biodiesel. In fact, India was the pioneer, but that biodiesel, you cannot use, for example, in an aeroplane, because that biodiesel tends to solidify, at a temperature of around, say, around minus 5 degrees centigrade. I mean, if you do add some, put some additives and all, you might be able to take it to about minus 10 degrees centigrade. That's about it. But beyond that, it will solidify. And we'll discuss that biodiesel. That is the conventional biodiesel. Okay. Now, what has been done is, you can see this was a Boeing 747, okay, which was run on this biofuel made from the Jetrofa plant. But this biofuel is a different biofuel, and this biofuel is basically this. It is obtained through this process. So effectively, you make a bio crude and then do catalytic hydrotreatment, okay, and you convert it into fuels, which are more like our kerosene, petrol, etc. And in fact, the automobile, not the automobile, the aeroplane fuel has a very unique property that it is highly branched. And because of being highly branched, it does not solidify. It remains liquid. Like if you're flying, you'll see that when they are announcing that we have now reached a height of some 40,000 feet or whatever, and the temperature outside is minus 35 degrees centigrade. Okay. Now, unless you had that kind of a special fuel, it would solidify and you would not be able to use it in a plane. Okay. So this fuel was effectively obtained by that kind of a hydrothermal liquefaction technology. All right. And so just keep that in mind. And this, of course, was used as a 50-50 blend. That is 50% of that biocrude derived oil, and 50% was conventional jet fuel. But it was the first time, this was about 12 years ago, right, that this trial was done, and just so that you have an idea, of how important this kind of hydrothermal liquefaction is. Okay, now I will not read this fully, right? But what I've done is that I have given you this thing from which you'll be able to find out what are the kinds of catalysts, etc., which are used, in this kind of hydrotreatment process. You understand? Okay. Now, let me also tell you that I can actually take something like, as I told you, wet biomass, refuse, etc. But what happens is that if I take that kind of cellulosic biomass, then my requirement of hydrogen becomes much higher. Okay? On the other hand, if I take a oil, you can get, like I can take peanut oil, groundnut oil, soya oil, because those are primarily CnH2n type of molecules. Only at the end there is a fatty acid. Okay, so the requirement of hydrogen is very nominal. Okay, in those kinds of cases, and so people, of course, prefer to do this kind of hydrothermal liquefaction with the oils rather than with the cellulosic biomass. But then I feel that it just defeats the purpose. The advantages of the process in terms of being able to treat wet biomass, etc., those are gone. When you do this, I mean, it's okay, for special requirements, as I told you, when you need to operate in a very low temperature, cold climates, you may require it. But there are so many applications, where we need diesel in regular applications, road use, So I think we should first try and make those things, before we start making all this aeroplane fuel and all, because there is so much of energy expended in doing all this. So you have to do a balancing. How much energy did I spend? How much energy did I require for my process? And how much did I get out? Okay. If that is not very attractive, then doesn't matter how great all these products are, it may not really be such a wonderful thing at the end. So bear this in mind, okay, while taking a decision as to what you should do with the biomass. Okay, but let me tell you some of the virtues, and this is, by the way, it is done by the work that I'm describing to you by one of the leading labs in the US, the Pacific Northwest lab, and so all of their data would be highly reliable. Okay, so you can see 350 degrees centigrade, 20 megapascal, which is about 200 bar. Okay, and the residence time is low, so you can actually finish the job quite fast. But unless you have a way of continuously feeding, it would be very difficult, to do this kind of a operation. Okay, you get a high carbon efficiency, that is 50% of the biomass carbon ends up in my product. It is very robust. That's a fact. I can take all kinds of biomass, and do a liquefaction. So in terms of, this is probably the best in terms of that kind of a flexibility in using biomass. Conceptually simple, but technically not simple. I mean, obviously, if you look at it conceptually over here, it all looks simple, unless you start asking, hey, you have to put in hydrogen. Where is this hydrogen coming from? Where are you getting hydrogen from? How are you taking out product, and how are you feeding more product in? What is the process by which you do it? Okay. So all of that stuff you need to look at. And here, what I told you about, one of the biggest advantages is wet feedstocks. I can take wet materials and I can process it. And we will come across another case where you can do wet feeding, and which to me is far more intelligent than this, okay, but it's done by nature, okay. And and finally, you can see the proof of the pudding is in the eating. What does it say? HTL has not been commercially deployed. Impediments to overcome include pumping to high pressures, scalable reactor configurations, and high capital cost estimates. Okay, so it's all great. You might make pilot plant, you might even make a few thousand tons of fuel, to run pilot experiments. But if I have to make millions of tons, then you have to ask yourself. But if there is some technical solution and someone comes up with something smart, then yeah, it's possible, that we might be able to do it in the future. Okay, I have more or less said the same thing here, but giving you a little more detail. Okay, I want you to read up the details. Okay, I'm not going to read it up. Okay, I have also given you the reference. You might want to look it up, right? But this is the broad details of the hydrothermal process, where you can actually see a little more of actual experimental details. Okay, now let's come to the last part. What did we say is a great thing about hydrothermal liquefaction? One of the big things, nice things, is that I can use wet mass. Okay, and that's exactly what I can do when I ferment biomass, right, to make biogas. I can take, in fact, one of the things which is used, especially in Maharashtra, is very important, is that after you distill ethanol, and what you're left with, that it's called spent wash, okay, and it's got a fair amount of organic still, in that liquid, okay, and so you don't want to get rid of. In fact, disposing that liquid is a big problem, okay. And so what people do, all the bio mills, all the biorefineries in India, and I'm sure all of those in Maharashtra will be doing it, is that I generate biogas, out of it. Okay, I just ferment. What is biogas? Biogas is nothing other than methane. It's CH4, no? And we saw like natural gas is CH4. Biogas is also predominantly CH4, a little more complicated. It requires some purification. We'll come to that. Okay, but let me tell you how smart biogas is compared to all this hydrothermal liquefaction and all. You see, it is not just that I can process wet mass. That's one. Okay. Second is methane is not soluble in water. So it will come out as a gas. So I don't have to spend money in distillation, all these things. I don't need to do. It just automatically will come out. Okay. And I then have to just do a purification, and then if required, I have to do a compression, or if I'm using it locally, I can just feed it to a burner or whatever. Okay. So let me show you, okay, how simple. And so where is 3000 psi and all this? And look at this. Okay. Room temperature operation. Okay. Look at what this guy is doing. Okay. Can you see this? It looks like a pillow. Okay. But it's the size of, it goes to some 50 feet, 100 feet, length, and maybe about 10 feet in height. Okay. It's massive. Okay? It's made from special types of textiles. Okay. This kind of stuff. And so what you do is you feed your biomass. This is like your reactor. Okay. You feed your biomass inside, and you have to put some things like gobar or something to initiate the whole process, okay, and then just leave it, okay, maybe for 20 30 days, and this whole thing will start filling up like a balloon, okay. This can withstand maybe about a couple of bar pressure, so you can generate large amounts of biogas, okay, into this, and then you move it wherever you need to move it, okay. And then what you do is that after you have used up the biogas, okay, all the rest of the material, the residue, you can collect. It will be wet, okay. You can use it as a fertilizer because you're just using biomass, and doing it. It's an excellent fertilizer which you can use in the fields, okay, or you can dry it up, okay? And then your biogas which you are collecting, as I told you, you can compress it and use it. You can use it in your car or somewhere, else. And but most biomass have some sulfur content, okay, and because biogas process is an anaerobic process, so it's under a reducing environment. So what happens to the sulfur is that what will happen to the sulfur in a reducing environment? Well, sulfur will end up as H2S, okay. When I'm in an oxidizing environment like combustion, so what is happening? My sulfur is ending up as sulfur dioxide and sulfur trioxide. When I'm in a reducing environment, there's no oxygen, okay, and I've got hydrogen. I'll show you where it's coming from, okay, and so it will end up forming H2S, okay. So that H2S, normally, a lot of people don't care, but obviously if I have to run a car, etc., with let's say instead of CNG, compressed natural gas, you'll call it CBG, compressed biogas. I've not heard that term, but I think we can call it CBG, compressed biogas. Okay, and so you'll have to clean up. Okay. Now another is that any fermentation process also generates carbon dioxide, because respiration is also taking place at the same time as the fermentation process is going on, and so the carbon dioxide is substantial, the amount of CO2. Now, if I have to compress my biogas, if it was a pure biogas, only CH4, I mean, obviously my cost of compressing would be less. But imagine if I have to compress so much of CO2, I mean, what's the point in compressing CO2 and spending money? Okay, so there is a need to separate methane and CO2 and H2S, in case you want to do a compression of the biogas and want to sell it in cylinders, because that would be the most energy efficient. Okay, so you need to find out simple means of basically taking that CO2 out. Like I can use an alkali, I can use lime, things like that, and I can remove the CO2. Okay? Or I can use triethanol, triethylamine, and take out CO2. Okay. Now, in fact, I this was just out of curiosity, and I was chairing a meeting in Delhi, right? And in fact, it's interesting. Just as we are trying to make biogas, methane, right? There's also a huge effort, right, to actually prevent methane formation. Where, for example, here I've put it in a closed environment, so I know my methane is in a closed environment. Okay, but what happens is that you don't know, or you may know this, but any of these, cows or buffalo, all right, the ruminants, okay, they release something like 70 to 120 kilograms of methane into the atmosphere each year. you can't put them inside this inside that balloon, right? I mean, they're just letting off their methane into the atmosphere. And methane is 25 times as potent as CO2 as a greenhouse gas. So if you just let out methane into the atmosphere, you're causing havoc. And in fact, there's a huge amount of research, going on, right, in how to kind of tailor the diet, of these cattle, right, so that they produce less methane. And in fact, one such formulation had been developed based on a seaweed technology, but you can see the conclusions, and it's by whom? Is by the Indian Council of Veterinary Research. This is the Veterinary Research Institute in our country. Okay? And so what they've said is that supplementation of both this and this. These are some additives. Okay, reduce methane emission. Okay, and so that's great. So while we are trying to produce biogas, a lot of people are also trying to suppress biogas. Or if there was a way of linking up the cattle to some kind of pipeline or something, so that the methane that they're emitting is basically going through that pipe, that would be marvelous. But I don't know; it will be a difficult technology to look at.